3, 2, 1. Boom. Capturing. Let's go. All right, let's learn things. All right. Okay. So, what's the goal for today? So, last time we introduced a bunch of stuff, but the big thing was that we introduced the idea of sets. This will be the first math topic we hit. We obviously set up, broadly speaking, kind of the main goal for the course, which is solving systems of linear equations. And part of that, when we say solve, means describe the set of solutions. So tell me what they look like. Right, but those things are sets, and sets have certain ins and outs that we saw. And now what we're doing right now out of the book is covering the preliminary section. So it has information on sets, which we more or less hit everything. But then also has information on complex numbers. So like I teed up last time, sets, right, goal for today is to go a step further and talk about the sets of numbers. Got to do some no end. There we go. Hey, look at that. Okay. So, like I set up, there are several sets of numbers that are of the utmost importance in mathematics. And for us, there's really only kind of three that are the major ones. But we'll talk about some of the intermediate ones. But the big one that we're going to discuss is that beautiful set right there. Is this size good? Do I need to zoom in more? Anybody want it more zoomed in? Okay. All right. Everyone can read. It's good. All right. Sweet. What? Yeah.
They changed last minute.
What?
Gave me the wrong number.
Oh, okay. You're good. Yeah, everybody in the room? So, actually, this is Thursday for the 1 o'clock, and there was a weird thing that went on with the workday. Had the weird Monday, Tuesday, Wednesday, Friday pattern for whatever reason. I don't know. So, yeah. Maybe. So, I saw some people who can't even believe it. I was like, uh-oh. But, oh, okay. All right, so our first one is that, good old n. So, this is the set of natural numbers. Okay. All right, so here's a question for everybody. What are the natural numbers? What's in this set? Give me some examples.
Are we putting zero in this spot?
Okay, so the big fight is, all right, where do we start with the natural numbers? So there are ones that are undoubtedly in here. Set of natural numbers. So it for sure contains a few numbers that we're familiar with. So for sure we've got 1, we've got 2, we've got 3, we've got 4, and successively beyond that, right? 5's in there, 6 is in there, 7's in there, 8's in there, 9's in there, right? Take any natural number, add 1, we're still in there, right? It's kind of the defining property. There's this succession that you can do with it. So you're always able to just, given anything in it, we can always go to the next one. All right, but there's a big old question, and it was already asked. Let me do this on another line. I don't like how that looks. All right, but big question. All right, what about 0? 0 in the natural numbers? What do you think?
I would say yes. We just use positive integers if we want
Positive is a...
Well, positive or non-negative.
No, right. So non-negative is the more you gotta be. So it's what's really annoying with that is there are mathematicians that use the word positive to include 0. Yeah. So so there's a branch of math, lattice theory, and if you're looking at things called lattice groups, you'll talk about the positive elements in there, and it includes 0 because they want the additive identity. Yeah. So, right. So, natural number, right? Natural, right? There's this like appeal to nature, right? This sort of like there are certain things in math that are like not weird or esoteric, right? They're naturally occurring, and zero seems pretty naturally occurring, especially if we're thinking about kind of the key property that we pointed out, this succession, this sort of like adding. And zero's got a very important property when it comes to adding. It doesn't do anything. So some people want zero in there. I am not one of those people. I am zero get out. And I think that's from my research background. So in terms of mathematical research, like the world I'm coming from analysis. And in analysis, right, we take a lot of limits of things, and we take a lot of limits of sequences, and we do a lot of series. And a lot of the series we want to start adding with 1, because we're doing a lot of 1 over n techniques. So we kind of want to start with n because we don't want it to be dividing by 0. Start with 1 because we don't want to divide by 0. So like my lived math experience has taught me that 0 isn't in here. But some people are all for it being in there. If you want to add 0, some other notations that are out there that people will use to indicate that, hey, I'm talking about 1, 2, 3, 4, 5, 6, and so on, and also 0. So a super common one is this one, n sub naught, which is the one that my advisor was all about, and so that's the one I use. A cool one that I think is really neat, and want to get into the habit of using is, so note for n, we have like this fancy symbol for it. We call it the blackboard n, because like when you, and now here's for the audio people aren't going to get this one. Right, when you draw it, right, you make an N, but then you put like an extra line like on the blackboard. So in LaTeX, you can make these symbols with math BB, or BB is supposed to stand for blackboard. So I had a student a while ago, and they were like, I use blackboard W to include 0. And by W, I mean whole number, right? So like there's a distinction between when you include 0 and when you're not. And I like that because it's sort of like, oh, like you remember your school days, like W, like for whole numbers, you kind of learn that it's like 0. Oh, okay. Because positive, depending on who you're talking to, has a weird, some people include 0 because, whatever. All right. Now, following this discussion, let's talk about the next set of numbers. And this one is for sure not a controversial collection, and that is the set of integers. So the integers, right? When we say integer, everyone knows what an integer is. There's like no room for debate. Right? Nobody's going to come in and go like, well, actually, 3/2 should be an integer because, like, no lunatic, right? No mathematician's going to do that. A physicist might come in with some garbage, but we're not going to do that math. So the integer is completely unambiguous here. Right? So when I talk natural numbers in this class, I will start at 1. Some people start at 0. It's fine. But the second one, the integers, this is right. You've got 0, you've got 1, 2, 3, 4, and beyond, and then you have the negatives. Okay. Now, the interesting thing, of course, is the symbol that's used, this z. Right? For natural numbers, we kind of had n, and then, like I said, I got w for the whole numbers, kind of like that. Anybody know why we use z for integers?
Comes from German.
It's German, yeah, exactly. So, specifically, the Z is supposed to be for the German word Zahlen, and I don't speak German. I never learned German. io parlo non bene Italiano. So this is as far as I go with the languages. Which again, that sentence actually isn't even like grammatically correct. The right way of saying it would be non parlo bene l'Italiano or something like that. Anyway, so I don't really know, but I know in German Zahlen doesn't exactly mean integer. It like means quantity or amount, and like context dependent has different meanings. But that's why we use the letter Z for that, and that's a good rule of thumb in general. Whenever like a weird symbol shows up, and you're like, why are we using this? A good chance for the reasoning for it is, well, German mathematicians were doing it in the 1800s, and during the 1800s there was a huge upheaval in mathematics and in the way it was done, and a lot of it was happening in Germany. So, just how it is. Also, sometimes French is things that will show up. Like, so for example, we're going to talk about row echelon form, and echelon is like French for stairs or something like that. Or something like that. I'm not sure. So every time there's like a weird word in math that shows up or a weird symbol that's used, yeah, the history math tends to be a little Eurocentric. So Germany or France are to blame. There are other countries that'll show up that'll screw everything up for us, but it's always fun to blame the Germans. So, all right, cool. All right, now before we continue. Our rundown of integers, of more numerical sets. So like I said, there's basically three of them that are going to be of the most importance to us. Now, integers are going to matter, we're going to use them, but we're primarily going to care about the natural numbers, because the natural numbers have a key property. And it's the following. All right, and here we go. Oh, I didn't do my no indent. Oh, and I got an error. Oh my god. Oh, because I didn't spell indent right. Cool. All right. So the key property of the natural numbers is as follows. If I give you a subset S with the property that 1 is in there, and that n plus 1 is in there for any n that's already in there, then what you got there is the set of all natural numbers. Right, and that makes a lot of intuitive sense, because if you think about what could S possibly have in it, well, we know for a fact it has 1. And then I told you that anything that's in there, I can add 1, and it doesn't escape the set. So I know I have 1 for sure. The first domino is set, and I know that I can then get the next one, so I know I can get 2. And hey, I have 2. I know I can go to the next one, I've got 3. And then I've got 4 or 5. Yeah, there we go. All right, yeah.
Can a set be a subset of its own self?
Yeah. Side note. Okay, we'll keep talking about this, but side quest. Yes, every set is in fact a subset of itself. Right. That's a weird thing to think of, because like in your mind, subset is supposed to be like a increasing, right? There's more things on the right than there is on the left. But that's not true, right? Because remember, two sets are equal if they're subsets of each other. Well, a set's obviously equal to itself, so it's going to have to then be a subset of itself. Right, and if you think about logically, right, given an element x that lives in A, well, it's an A. There you go. Right, the implication is true. Following that was a great question. I'm gonna say this is a bad follow-up. So the fundamental ingredients of sets are equality and membership. Obviously, a set is always equal to itself. Can you make a set that is an element of itself? And this has the best answer ever. So depending on the rules that you decide that sets need to abide by, you either ensure that no set can be an element of itself, and just naturally try to envision what that would even look like. So the usual rules for sets are, they're called the Zermelo-Frankel axioms, usually from something called the axiom of choice, so it's usually colloquially referred to as ZFC. In ZFC, A is never an element of A. So every set is not an element of itself. That's just not allowed. However, other mathematicians have come up with other rules for sets, and there are other rules that allow this to happen. So, for example, there is something called New Foundations by a mathematician named Quinn, and he allows for things to exist like this. He calls them Quinn atoms or something like that. They're called, I don't think he deliberately named them after himself. Other mathematicians have pulled that one off, though. But, yeah, so, yeah, cool. All right, so look into that. It's good stuff. All right, a little beyond what we need to talk about. All right, key property of natural numbers is this one right here. And what's the name for it? Anybody remember? When I have got my first thing, and then I show that if I have something, I can get to the next step. This is the proof technique. Hey, thank you. Yeah. All right, so if you haven't taken 201 yet, or if you're concurrently taking it, I'm spoiling part of the course. But all right, this is known as induction, or mathematical induction if you want to be like really precise. Okay, so it is an incredibly powerful proof technique if you want to establish that something is true, and it involves, hey, this works for all of the numbers 1, 2, 3, 4, 5, and beyond. Induction is usually a great way of proving that. So let's do our first mathematical proof, and it'll be a good old induction one. All right. And we'll do the all-time classic, so you may or may not have seen this. But if not, we'll work out the details of it. So all right, so the classic induction that everybody does, the first learn it, is that if I add up the first n numbers, there's a nice closed form expression for this. It's n times n plus 1 all over 2. Okay. So this is what we'll prove. So note the notation that I used here. I used this sort of additive notation. We could also write it using everybody's favorite math notation, sigma notation. Right, indicating that I am going to start when k is equal to 1. I'm going to go up to n, and I'm going to add k. So I add 1, I add 2, I add 3, all the way up to n. Okay. So we're going to be doing a lot of adding, and there will be a lot of sigma notation. So sigma notation you hopefully saw in Calc 1, and played around with it a little bit. It definitely plays a huge role in Calc 2, because Calc 2 we get into series. You're not going to get into the series. This is finite dimensional linear algebra. In infinite dimensional linear algebra you do series, which is my mathematical background, like I mentioned. So, good stuff. All right. But let's go ahead and do this proof. So we're all comfortable, first of all, with how proofs are supposed to look, and also so we're good with proofs in using induction. It's a technique that we're going to apply quite often. Not just this math class, but probably every other math class you'll take. You're going to do inductions, whether you like them or not. All right. Now, when it comes to inductions, a lot of people have very rigid rules of you got to write base case induction hypothesis and really sell it. I'm definitely more of a fan of just write it. Just tell me what you're doing and be clear. Right? If you go hey, I'll prove this is true for n equals 1, and now I'm going to suppose it works for n and show it works for n. I know what you're doing. You don't need to announce everything. But if you do want to let people know, you can do that. I also like this phrase. This is one of my advisors. We proceed inductively. So let people know you're going to do induction. Yeah, it's good stuff. So note the way I'm doing proofs, I'm using the proof environment of LaTeX, so I got the nice little square at the end. So the square at the end of a proof is a pretty modern thing in mathematics, and it's one of those interesting math notation things where you can kind of point to the exact person that came up with this. When proofs were done back in the day, they would end with QED or something similar to that, because Latin's cool. But the box at the end, this is actually due to a mathematician named Paul Helmos. He was a fan of ending his proofs with a box for whatever reason, and it just caught on. And now it's how we do it. All right, so let's actually do the proof now. So repeating direction. All right, so first base case, what happens when n is equal to 1? All right, so just replace n with 1, and we'll see what happens. All right, so go to our sigma notation. I replace the n with 1. All right, well, what does that actually equal to? Oh, it's just 1. Right, the sum says start at 1 and end at 1, and use k. All right, well, I started at 1 and ended at 1, plug in 1. Nothing interesting going on here. All right. Now, what does that actually equal to? Well, know what I want it to equal to. I want it to equal n plus 1 over 2. So note that 1 is sneakily equal to some other stuff. It's equal to, for example, 2 over 2. And the 2 in the top, conveniently, I can write as 1 plus 1 all over 2. Hey, all right, there we go. Base case taken care of. My claim, I want to be a little more. And let's make my proposition a little bit more precise. So I've got this summation, and it holds for all n out of the natural numbers like that. Okay. All right, so base case taken care of. Plug in 1, life is good.
It's not the same when you plug in 2.
Right, there's no need to plug in 2, right? So for induction, we need to show 1 works, so we need to show 1 explicitly works. Sometimes you start at 2, right? And you're like, plug in 2 and show that works. Now that we get the base case taken care of, now I want to show that if it works for n, it works for n plus 1. So that'll be what we do. So now, suppose that my proposition is in fact true. For some n out of the natural numbers. Okay, so for any n satisfying the property, I want to show that n plus 1 will also satisfy the property. Okay, all right, so now to use the same n here, if you want to be maybe a little bit more careful or keep things a little more straight in your head, you can use a different n. So for example, like a capital N. So, for example, maybe you write that. So, right, just so it's like, well, this is like for all n, and here I have an explicit n I'm assuming is working, and I'm going to show n plus 1 works. So if you want to make like that sort of notational delineation, again, really doesn't matter what symbols you pick or use. Just be consistent with them. Right? That's the mathematician's burden, right? So in philosophy, you spend your entire life arguing about what is a chair. But in math, we agree on what a chair is. The thing we fight about is, well, what symbol are we going to use to denote a chair? I like this one, and it's best because I said so. That's so. In academia, everybody's just having the exact same petty argument, but the context is different. Okay. All right, okay, so now we suppose it's true for n. We want to show it's true for n plus 1. So let's start setting that up. Okay, there we go. All right, so now I want to show that the formula holds with n plus 1, which means that I need to verify that this is in fact equal to, replace this with n plus 1, or replace that with n plus 1. So let me write my ending that I want. And then I'll figure out how I get there. All right, so this is a pretty good proof strategy in general, where you think about what you know is true, and you think about, well, okay, what do I want to get to? I want this to equal that, right? Because then I've proven that, well, if n works, then n plus 1 works, and that takes care of the induction. Okay, so I want to show that I can actually do a chain of equalities here and get from this to that, and that completes the induction. All right, so the key thing here is to remember what we've assumed. I've assumed that when I add up the first n things, life works. Okay, well, how do I extract that information from here? Well, this summation is 1, 2, 3 up to n plus 1, so it crosses n. And in fact will equal that. Right, so that's kind of the key characteristic of the summation notation, is that it's telling you that, hey, if I add up stuff, I can peel off a term, and I still have whatever I added up, but then I've got the next term. Okay, so this sort of breakdown here is the key property of how sigma notation works, and we're going to basically, whenever we have to exploit sigma notation, is what we're going to do. We're going to go, all right, peel a term off, or do a little re-indexing, or swap some summations. We'll see all of those techniques on display as the semester goes on. All right. Now, the reason that this is a good step is that this thing right here, I actually know what that's equal to. I told you it's equal to that. So I can plug this in. I'm allowed to substitute because I know those things are equal. Hey, all right. Now, I'm not done yet because this from here to here, while it is in fact true, right now it's a bit of a jump, right? It's not clear how this turns into that. So let's make that clear by doing a little arithmetic, God forbid. All right, well, I've got a fraction over 2 on the left, but I don't have that on the right, so let me go ahead and multiply top and bottom by 2. Dirtiest math trick in the book, multiply by 1. Right. Basically, all of math is like Atlas holding up the world, and Atlas is add 0 or multiply by 1. That's a left side, right side. That's what holds up the math world. All right. Okay. Actually, and let's make our lives a little easier, I already distributed the multiplication, but let's actually undistribute it. There we go. Because now it's going to be really clear how we go from here to here. Note that now my denominators are the same, so I can combine the summation. Into one fraction like that. And then now here, there is a common term. There is an n plus 1 and an n plus 1. So I can factor that out. And if I factor that out, I'll get my n plus 2. Sweet. All right, and there we go. Now those collections of equalities are legitimate. We have proven the claim, and we use the induction. Yay. All right. All right, what's next? All right, so now that we've gotten a little play with integers and the natural numbers, note something interesting as a side effect of this proof. Note that if I add up a bunch of natural numbers, I remain natural. I'm still an integer. This right here is a fraction, but because it's equal to a sum of integers, it has to be an integer itself. So we incidentally proved that n times n plus 1 all over 2 is always a positive integer. Now, you could directly prove that because 1 of n and n plus 1 is divisible by 2. If n is even, then you're divisible by 2. But if n is odd, then n plus 1 is even, so that's divisible by 2. But as a side effect, we prove that. However, it's worth noting that there are things that are looking like this, but are not actually integers. So, as I mentioned, 3 halves. So that set of numbers, that collection, these are called the rational numbers. And Q is the symbol we use for it. And here is another spot where I like my natural numbers to start at 1 rather than 0, because I can neatly represent rational numbers as a ratio, hence the name rational, as an m over n, where m is out of the integers and n is out of the naturals, so I'm not dividing by 0. And note here, I only have positives down in my denominator. So if we do have a negative, I've already thrown it up in my numerator, which I think is how everybody would typically write a fraction. You would write negative 3 over 2, or maybe you're a grade A lunatic and you write 3 over negative 2. All right. Now note the Q here also makes some sense, Q for quotient. So that doesn't have a mysterious origin. All right. Now, we're not going to get too sweaty about rational numbers. They'll appear, but we're not going to need to care too much about them. When you take Math 414 analysis, oh yeah, rational numbers are, yeah, you got to be worried about them. So depending on the branch of math you're in, you're worried about them. But we're not going to get too, they're there. We need a symbol for them, but they're not going to be a big part of our life. However, the next set is life. The real numbers. So the blackboard R. Okay. The real numbers are life. The real numbers are love. This is where we live. So the real numbers are basically the number line. So if you envision in your mind a line that extends out indefinitely in both directions, and in the middle you've got 0, and then you've got 1 and -1, 2, -2, right? Just kind of think of this like infinitely long ruler that has 0 and positives and negatives. Then you can put in the halves and the quarters and the thirds, so on and so forth. You can put all the rational numbers in there. But if you do that on that number line, you're going to miss stuff. So the most famous example is good old square root of 2. Square root of 2 is, in a sense, a measurable quantity. It's on the number line, right? Right. If I draw a triangle with a base and a height of 1, then that hypotenuse by Pythagorean theorem, big old root 2. So root 2 is out there as like a measurable quantity. It's irrational, though. It's got an infinitely long decimal expression that doesn't repeat. But it's a real number, right? You can kind of envision roughly where it needs to be. I can draw a geometric figure to tell you, hey, this is out there. So the real numbers take the rationals, then just fill in the rest of the gaps to get the rest of the number line. Right, and there are a lot of other real numbers that fail to be rational. E, for example, is irrational. It takes a little bit of effort to prove that. Not too much, but it's not too bad. Pi is irrational, and proving pi is irrational is a big old pain in the ass. Oh my god. The easiest way to do it is like set up these wild integrals and then just like magically, it's like, oh, it can't be rational because these integrals do weird stuff if it is. All right, but there's other interesting things out there. And for the most part, the real numbers are great, right? A lot of modern mathematics, right? Modern computing, right? You're doing stuff with floats. You got decimals, right? The real numbers are life. We use them for everything. Okay. And for our purposes, we're not going to build the real numbers from scratch, which is something you can do. So as I mentioned, the Zermelo-Fraenkel axioms for set theory, you can actually use them to create the real numbers from literally nothing. Like you start with the empty set, and then you create the set that has the empty set in it. That's 1, because that has 1 element. And then you take that set and like glue it to itself, and then you get 2, and then you go and you get all your integers. And you can follow all these sort of construction steps, and you can make the real numbers out of it. We're not going to worry about that, but the main thing about the real numbers that we're going to be interested in is their algebraic properties. So real numbers can be added and multiplied, and addition and multiplication behaves the way you think it should. So the first one that's worth mentioning is the associativity property of addition. It's sort of the unsung hero of addition. Because note, what does this tell you? That means that x plus y plus z, if I write that without the parentheses, that has meaning, right? That is only one possible thing. It does not matter where you plot parentheses. Addition is give me 2 things and I can add them together. And the associative property says that you can go beyond 2 things. You can add 3 things, right? And as we'll see when we do some more sophisticated matrix proofs with addition, we'll see that the associativity property is very powerful, very useful. All right, next up, commutivity, which goes without saying, x plus y is y plus x. But it's worth mentioning and pointing it out because there are things that fail to be commutative, right? In your math life, you know function composition is not commutative. Square root of x plus 1 is different than square root of x plus 1 quantity. Right, the order in which you compose square rooting and adding 1 matters there. And addition is always commutative, basically, but multiplication, as we'll see with matrix, is not quite. All right. What are the other key properties? So, as we've already mentioned, 0 has a very nice property. Adding it doesn't do anything. And related to that, there is a key thing that we can always do, and that is always find a negative. So given a real number, there is a negative of it, and it's got the property that adding it to itself gets us to 0. So in other words, addition always has inverses. Now, colloquially, when it comes to inverses and addition, we don't really think of it like that. We think of it as subtraction. But we do want to keep that in mind that it's really adding the negative. So when you do write x minus y, that's just shorthand for x plus negative y. Subtraction is an illusion. There is only addition. All right. And the next ones I'll fly through quickly here. So multiplication has a bunch of similar things as well. So for example, hey, we got the page 2. So for example, associativity of multiplication, commutativity of multiplication of real numbers. There is a multiplicative identity, 1. But for inverses, it's a little interesting because we got to throw in that, well, if you're non-zero, then you've got a multiplicative inverse because we don't allow for division by 0. Okay. And note here so far, out of these 8 axioms that I've enforced, the first 4 are telling me how addition behaves. The next 4 tell me how multiplication behaves, but I haven't actually told you how addition and multiplication interact with each other. And that's the last axiom, and that's the distributivity. Good stuff. Now, what do I got for time here? All right, I wanted to get to the complex numbers, but that'll be the plot for tomorrow. let's wrap up today by proving something that you know true about real numbers that isn't on my list here. And this will give you a feel for how you prove things with axioms in mathematics. Okay. Multiplying by 1 doesn't do anything. What does multiplying by 0 do? Gives you 0, right? 0 times anything is 0. Note, I don't have that on my axioms anywhere here, right? That's not included in my rules. And guess what? I don't need to include it because I can prove it from these rules. So when you're axiomizing things, when you're being very mathematically precise, you typically want to assume as little as possible, so enforce as little axioms as possible, and derive as much as you can. So there are a lot of mathematical facts that you know to be true about how adding and multiplying real numbers works. I'm telling you those 9 are the only 9 you need. Everything else can be proven. Now, proving every single thing might be completely exhausting and a absolute waste of time, but this one's a good, worthwhile one to prove. And again, this will just give you an idea of how proofs like this look and behave. So, I will begin this proof with my favorite word in mathematics, to use in mathematics, indeed. So I start a lot of my proofs with the word indeed, and I got into this habit from a professional colleague, Thomas Tonev. He's unfortunately no longer with us. And he was Russian, and my advisor was convinced that his beginning of sentences with the word indeed was some, the Russian thing or something he was trying to translate. But I was reading his work, and I liked proofs beginning with the word indeed, so I started doing it. My advisor saw me doing it. He's like, "You've been reading Tonev stuff, haven't you?" I was like, "Yeah." And he's like, "Stop doing it." And I was like, "No. This is who I am now. This is who I've always been. You just didn't know." All right, so I like starting proofs with indeed, and of course I share that with everybody that I learn proofs with. I had a student come to me later on. He's like, "I started a proof with the word indeed, and Professor Song got really mad at me." He was like, "What do you mean indeed? What is this word?" So, just saying, not everybody's cup of tea, but I like doing it. All right, so how am I actually going to prove this? Well, let's think about the axioms that I got, and let's note that this is kind of a statement that mixes addition and multiplication. 0 is the additive identity, and I'm multiplying it. So probably what I'm going to use is distributivity, because that told me how I can intermingle the two. All right, so how am I going to do that, though? All right, and again, let's start with what I had. Let's start with a starting point. Well, I got x times 0, 0 times x. Well, what do we know about 0? We know that it's the additive identity. So it is equal to itself plus itself. And now, while I only wrote one of the distributive facts, distributing across the left, you can distribute through the right as well, because note, multiplication is commutative. So this distributes to 0x plus 0x like that. And then adding the negative of that to both sides would yield what? Well, on the right, one of these would get deleted because you would add the negative and get 0, so you'd add nothing. But on the left, you'll get 0. And there we go. I've proven from my axioms that multiplying by 0, in fact, gives me 0. Yeah. There you go. So, to quote Bart Simpson, what's 5 million times 0? Don't tell me it's 0. Or a million, I forget exactly how much. He had stocks in some company that went under, and then he was trying to figure out what 0 times it was equal. He yelled at Lisa, "Don't tell me it's 0. That one always stuck out of my head. All right, but indeed it's true, and we rigorously proved it. So we had a couple proofs in today, give you an idea of the style I like to write proofs with and how we're going to do stuff. So, all right, we got to the real numbers. Tomorrow we will get to the complex numbers. we're primarily going to work with real numbers, but every so often we need complex numbers because, as you may know about them, they help us out with getting roots of polynomials. And every so often we need to get roots of polynomials, and we need to always get roots, so we need complex numbers. All right, that's the story for today. I'll see you tomorrow.